Hello and welcome back to our channel. Today we'll be doing question 7 from the 2014 MAT. This is a question for computer science and philosophy or computer science applicants only. Question 7. A finite automaton is a mathematical model of a simple computing device. A small finite automaton is illustrated below. A finite automaton has some finite number of states. The above automaton has 3 states, labeled S0, S1 and S2. The initial state, S0, is indicated with an incoming arrow. The automaton receives inputs, for example via button presses, which might cause it to change state. In the example, the inputs are A and B. The state changes are illustrated by arrows. For example, if the automaton is in state S1 and it receives input B, it changes to state S0. If it is in state S2 and receives either input, it remains in state S2. For each state, there is precisely one outgoing arrow for each input. Some of the states are defined to be accepting states. In the example, just S1 is defined to be an accepting state, represented by the double circle. A word is a sequence of inputs. The automaton accepts the word W if that sequence of inputs leads to an accepting state from the initial state. For example, the above automaton accepts the word ABA. Part 1. Write down a description of the set of words accepted by the above automaton. A clear but informal description will suffice. Part 2. Suppose we alter the above automaton by swapping accepting and non-accepting states, i.e. we make S0 and S2 accepting and make S1 non-accepting. Write down a description of the set of words accepted by this new automaton. Again, a clear but informal description will suffice. Part 3. Draw an automaton that accepts all words containing an even number, possibly 0, of A's and any number of B's, and no other words. Part 4. Now draw an automaton that accepts all words containing an even number of A's or an odd number of B's, and no other words. Pause the video to have a think and watch it ready restart to see if you're right. Let's get started. We'll see that the word A leads to state S1 from state S0, which means that it's accepted. The word ABA is also accepted. So is the word ABABA. We can continue this pattern and we'll see that all words consisting of alternating A's and B's, starting and ending with A's, are accepted. Part 2. This is quite easy because any word that's accepted by part 1 will lead to a non-accepting state, and every word that's not accepted will lead to an accepting state. So the answer to part 2 is simply all words that are not accepted by the original. Part 3. Any automaton like the one below should work. Let's start from S0 and follow the paths. A single A will lead us to S1, and then another A will lead us back to S0. We can repeatedly follow this and see that an odd number of A's will leave us at S1, but an even number of A's will take us back to S0. We then look at the arrows for B. All arrows for B lead back to where they started, so this automaton does not care how many B's you have in your word W. Part 4. Any automaton of this form should work. Using De Morgan's laws, we should see that this automaton shouldn't accept things with an odd number of A's and an even number of B's. This, of course, is precisely what it does not accept. An odd number of A's and an even number of B's will take you to S1. Therefore, this automaton is one of many possible correct answers to part 4. Part 5. Let A to the n represent n consecutive A's. Let L be the set of all words of the form A to the n, B to the n, where n equals 0, 1, 2, etc. i.e. all words composed of some number of A's followed by the same number of B's. We will show that no finite automaton accepts precisely this set of words. Suppose that a particular finite automaton A does accept precisely the words in L. Show that if I does not equal J, then the words A to the I and A to the J must lead to different states of A. Hence show that this leads to a contradiction. Pause the video and have a think and watch already restart to see if you're right. Let's get started. Since A to the I, B to the I, and A to the J, B to the I lead to different states of A to the I and A to the J must therefore lead to different states of A, if they lead to different states after B to the I is applied to both of them. Therefore, each word A to 1, A to 2, and A to 3 must lead to a different state. However, this leads to an infinite number of states, contradicting the definition of a finite state machine, meaning that A does not exist. And that's the answer to part 5. If you liked our video, please like and subscribe, and we'll see you next time for more fun videos.